So, welcome to the lecture on transient response analysis. Today we will discuss in this lecture about poles and zeros. So, in previous lectures we have discussed that to design a control system we have three objectives. First one is the transient response, second is stability, and third is steady state error. So, we saw that transient response is defined as a system's characteristic because it is governed by the system's internal characteristics, transfer function. And we test the system's response with some defined input such as unit step input or impulse input and so on. So, today we will discuss about poles and zeros because and link these poles and zeros to the transient response characteristic of a system. So, the poles and zeros, they simplify the evaluation of system's response. So, let's define what is pole and what is zero. So, we have a transfer function so we have this transfer function Gs. It is subjected to some input and it is giving some output. So, this transfer function Gs can be written as Ns by ds. So, Ns is the numerator part of the transfer function and ds is the denominator part of the transfer function. So, from the transfer function, how can we get the poles and zeros of a system? So, poles or poles of a transfer function or the values of Laplace transform variable s. So, values of s that cause the transfer function to be infinite. So, the values of s for which the transfer function will become infinite is the pole, or we can say that if we can put ds equal to 0, this will make this transfer function infinite, and ds equal to 0 will give the values of s. So, the roots of this equation ds equal to 0, that is the values of s or the poles, because these values will make the ds equal to 0 and so the transfer function to infinite. So, now come to the poles or all the roots of the denominator, all the roots of the denominator of a transfer function so here denominator we say ds. Now come to zeros. So, zeros of the transfer function or the values of Laplace transform variable s that causes the transfer function to become 0. So, when this transfer function, all the values that makes this transfer function 0, so that is ns equal to 0 If n is equal to 0, this transfer function will be 0. So when we solve this equation and we find s, these values are the zeros. So zeros are all the roots of the numerator ns of a transfer function. So here we have defined the poles and zeros. So let's take one example. So let's take that GS equal to s plus 2 upon s plus 5. So this is GS equal to s plus 2 upon s plus 5. So we want to know the poles. So to calculate the poles, we should, what is numerator, denominator ds equal to s plus 5. ds equal to s plus 5 and that equal to 0. This implies that s equal to minus 5. So s equal to minus 5 is a pole of the system or of the transfer function. Now we get the zeros. So here we have only one pole. Now come to 0. So to get 0, we need to put the numerator equal to 0. So ns equal to s plus 2 equal to 0. So this implies that s equal to minus 2. So s equal to minus 2 is a 0 of the system or transfer function. Now let's show these poles and zeros on a S plane, that is complex frequency plane S, or complex Laplace transform variable plane. So we can show it. This is S plane, and here S equal to sigma plus j omega, because S is a complex variable. So it is sigma is the real part or real axis, and omega is the y axis, and this is complex axis. So here if we want to show s equal to minus 5, so here we have only the real part. Here complex imaginary part is 0, so s equal to minus 5 we can show here. Let's show here, this is minus 5. Then 0, that is s equal to minus 2, so it will be somewhere here. Now there is representation for poles and zeros, different representation. So a 0 is represented as a circle, a small circle, and pole is represented as a cross. So here we have pole s equal to minus 5, here we show as a cross, and 0 we show as a small circle. So we have shown the poles and zeros of a system on the S plane. Now let's try to find that when this system is subjected to some step input, unit step input, what will be the response transient response and complete response, and how we can link it with the poles and zeros. So here we have, let's have this GS. So GS here is, okay, this is GS. So let's show this. This is S plus 2 upon S plus 5 . This is RS, this is CS. So let's RS is a unit step input, something like this. And so the Laplace transform of unit step function is 1 by S. So here RS equal to 1 by S. Now we have to find what is the response of this system under this input. So here we have CS equal to RS into GS, CS equal to RS into GS. So RS is 1 by S and GS is S plus 2 by S plus 5. So now we will use partial fraction to break this function. So A by S plus B by S plus 5. So we break these into two parts. So A and B are the constant or coefficient. So we can write this A S plus 5 plus B into S upon S S plus 5. So this we can write AS and BS, so A plus B S plus 5A upon S S plus 5. Now we compare this and this. So when we compare these, because this is SS plus 5 and the numerator here we find this is S plus 2. So A plus B equal to 1, because the coefficient of S is here 1, and 5A equal to 2, because this constant term 5A equal to 2. So here we get A equal to 2 upon 5, and from this equation we get B equal to 1 minus A, and that is 1 minus 2 by 5 equal to 3 by 5. So we can write CS equal to A by S. So A is 2 by 5, 2 by 5 by S plus B by S plus 5. So B is 3 by 5 by S plus 5. So this is the CS. Now if we want to, we have come from, now we are in the S domain. We have to come to the time domain to find the response with respect to time. So we take the inverse Laplace transform of this. So we will get Ct. So, we take Cs will Ct and 2 by 5. So, inverse Laplace of 1 by s is unity function. So, 2 by 5 plus here 3 by 5 and here s plus 5. So, here with s there is minus 5. So, it is e power minus 5 t. So, now here we can make some conclusion based on this. So, here we have input is 1 by s. So, Rs is 1 by s. So, here we have one pole that is s equal to 0. So, here s equal to 0 is one pole of the input. Then here we have at minus 2 one system 0. So, this is input pole, this is system 0, and this is minus 5, that is system pole. And we see that here Cs equal to 2 by 5 by s plus 3 by 5 by s plus 5. And here Ct equal to 2 by 5 plus 3 by 5 e power minus 5t. We can see this is the constant term. So, this is the steady state value and this is exponential minus 5t. So, that is the exponentially decaying value with the time. So, this is the forced response. And this part is natural response. We see that this value 2 by 5 is coming here, and there is this calculation to get this 2 by 5. Because this pole is coming here 1 by s. So, these values they are depending on the values of 0 and pole, and this value is depending on the input pole, and this term minus 5 that is coming from here, it is depending on this system pole. So, we see that the amplitude of the natural response value depends on the 0 and pole, while the form that it is exponential value is depending on the system pole, whereas this first part depends on the input of the system as well as this zeros also, because this value is coming by this calculation which include the 0 and pole. So we can, from here we can see the role of the system pole, system 0 and the input pole on the transient response as well as force response. So complete response of this system. So what we see that a pole of the input function generates the form of the force response. So because the input was unit step input 1 by s, it generated a response form of 2 by 5 by s, or we can say input was unity and it gave output, that is, so output is here T Ct and it is something, so this was the input and this is output 2 by 5 and this was the input 1. But the form is similar because this is also unity function, here it is also, that is step function, this is output is also step function. So the form of this output forced response is governed by the pole of the input function, and pole of the input function depends on the form of the input. Now come to this part. A pole of the transfer function generates the form of the natural response. So the form of the natural response is exponential here, and that is generated due to the pole of the system or the transfer function. So due to this system pole, this form is here. If this system pole is here, then this exponential part will not be there. So we can see that, or if we move this pole, we can see that the form will be exponential, but it will decay in the its speed of the exponential decay. So we conclude that the pole of the transfer function generates the form of the natural response. We see that the amplitude, these amplitudes are coming from this calculation where it involves both the 0 and pole. So the amplitude is depending, the 0 and pole generate the amplitude of both the force and natural response. So here we can, one more point we can note that, so if this is my system pole here at alpha on this axis, on the real axis. So if the pole is on the real axis alpha, it will generate a form e power alpha t. It will generate exponential response of the form e power alpha t, and where alpha is the location of the pole on the real axis. Moreover, this alpha will be farther, it could be far. So if it is far, this value will decay faster. So the transient response will decay to 0 more fast than less value. So if we this pole is moving, so here this is alpha 1, here is alpha 2. So e power alpha 2 will decay faster than e power alpha 1. So suppose this is my input Rs, that is equal to 1 by Cs. Let us say this is unit step input. Now I want that what will be the response of this system. So here Cs equal to Rs into Gs. So that will be equal to 1 by S, S plus 3, S plus 2, S plus 4, S plus 5. And we can write this as K1 by S plus K2 by S plus 2 plus K3 by S plus 4 plus K4 by S plus 5. So by using the rule of method of partial fraction, we can write this in this form, and we can find the K1, K2, K3 and K4, these coefficients. And so this is the forced response, and these three are the natural response. You can see these poles are these 2, 3 values -2, -4, -5, and these poles are giving the natural response. And so if we do CT, so we can write K1 plus K2 e power minus 2t plus K3 e power minus 4t plus K4 e power minus 5t. So here we can find the response of the system. So now we see that when there is a system, we can go in the S domain, we can write this output, then we can go we find these coefficients, we come back to time domain by taking the inverse Laplace transform. So now here today what we discussed about poles and zeros. So we summarize that the poles are the roots of the denominator of a transfer function, and zeros are the roots of the numerator of the transfer function. And we saw that the poles of the input governs the force response, the form of the force response, and poles of the system or transfer function governs the form of the natural response. And the values, that is amplitude of these responses, are governed by poles and zeros. And we saw that if there is some pole on the real axis, the natural response is in the form of exponential alpha t, where alpha is the location of the pole on the real axis. And we see that if the pole is on the negative axis, much farther from on the axis, then the decay will be faster, and so the transient response will decay faster. So these examples that we took from the book of Nice Norman as Control Systems Engineering. So I thank you for this lecture, and see you in the next lecture.